What we're going to do right now is explain this type of a solution. When we were solving examples where it says find all radian solutions, we weren't just getting two solutions or one solution like we did in other examples, but it still looks like just two answers, but they're written in more of an equation form. The reason we write these in an equation form is trigonometry is periodic. It's cyclic. That means that the same thing happens over and over and over again. So if I ask you when a certain trig graph, okay, or trig equation, say cosine, looks like this, okay? This is what one cycle of cosine looks like. And then it repeats itself again and again and again. So if I asked you, pretend this little window of it right here, and we'll get more into this when we graph, this little window of one cycle of cosine is showing you what it looks like between 0 and 2 pi if we were to graph it on the xy plane. But if I ask you, when does cosine equal negative radical 2 over 2? Well, cosine, the middle of it right here this is where cosine equals 0. If I wanted to know when it equals negative radical 2 over 2, that's going to be about negative 0.7. Down here, this is negative 1. Negative radical 2 over 2 is somewhere over here. So between, oh, that shouldn't be pi, I'm sorry, 2 pi. So between 0 and 2 pi, it equals negative root 2 over 2 twice. If this is cosine, all right, I'm not going to ask you to graph this right now. I'm just showing you like a visual representation. So negative root 2 over 2 is some steady amount. Between 0 and 2 pi, it'll equal it twice. The places where it'll equal are dependent on what this is over here. These spots right over here are actually 3 pi over 4 and 5 pi over 4. So if I were to kind of just go over here and just do a little color coordinating for a moment, 3 pi over 4, okay, represents that right over there. And 5 pi over 4 represents that over there. I know right now we might be sort of limited to picturing this on the unit circle, but I want you to think, I think this is an important comment that I'm making. I want you to remember that the unit circle isn't a graph of sine and cosine. I know it looks like it's on a graph because you have the x and y axes, but similar to the word graph, the unit circle is actually a graphic organizer. I don't know if you use the word graphic organizer. Teachers use it a lot. Graphic organizers are like those types of worksheets that teachers might pass out to students and you guys fill in boxes. Maybe you use it when you make a flow chart or you're brainstorming to write an essay. You have a central idea, ideas that branch off of it. Maybe you think of it as the chart at the back of a notebook that shows you, you know, all the conversions of meters, centimeters, kilometers, or all of your times tables or anything, right? We have these charts, the periodic table, okay? It's basically a graphic organizer. And that's what the unit circle is as well. It's a graphic organizer. The graph of cosine, though, is a wave. So it looks like this. If I only asked for answers between 0 and 2 pi, there we go, 3 pi over 4 and 5 pi over 4. But in part B, we're saying for all radian solutions. Well, the graph of cosine, right? If this is cosine, we said goes on really forever, indefinitely. It's like the seasons, okay? If we think of this as summer, fall, like temperature wise, summer, fall, winter, spring, repeat. Summer, fall, winter, spring, repeat. Summer, fall, winter, spring. Okay. So if we're like, oh, when is the temperature in New Jersey this amount? Okay. It repeats. You're going to see those temperatures in the fall and the spring, you know, every year or something like that. So if I want these other answers, this pink one right over here, what you do is you add 2 pi to it, because if I keep this line going, you're going to hit that answer again here and here, here and here, here and here. So other answers that I can generate from that first pink answer are there, there, and there. those are going to be able to be generated from this pink one right here by adding 2 pi. If I add 2 pi once, I'll get right there. If I add it twice, I'll land there. If I add 2 pi 3 times, I'll land right there. If I subtract 2 pi, probably should have left more room, I'll just go backwards in this graph and get one before it. Same idea with the yellow. With the yellow, if I add 2 pi n, okay, or 2 pi once, twice, whatever, this yellow will generate that answer, that answer, that answer forever. But since the answers go on forever, you can't list them, right? It's like writing a decimal like pi and answering as a decimal precisely. You would be writing forever. So we created a symbol as a way to represent all of the digits of pi, okay? So when you're solving, in this case, when it equals negative square root of 2 over 2, for all radian solutions, we see that it does go on indefinitely. We're not limiting to a window between 0 and 2 pi. We write a solution like this, where we add 2 pi n number of times, where n is an element in the set of integers. If you were to work this out a long way by hand and actually use it to calculate it, which sometimes you want this formula, it's going to be handy sometimes, we'll say integers, so these are my integers, so dot, 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 meaning in ellipses, like we keep this list going, -2, -1, 0, 1, 2, run out of room, dot, 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 close my little set notation bracket. I don't know if that's on the screen. All right, that is some integers. If I let n equal -2 and I fill it in this equation, I'll get theta equals 3 pi over 4 plus 2 pi times -2. What's 2 pi times -2? What's 2 pi times -2? You can participate here. Shout out, raise your hand. Easy moment. Go ahead, Jeremiah.
-4 pi.
Right. And if I'm doing -4 pi, I should probably, I'm going to kind of write over this in a minute, get a common denominator. Right now, 4 pi is over 1. What could I rewrite 4 pi as so it has a denominator of 4? I could rewrite 4 pi as what? So you could even participate in the chat if you don't want to participate out loud.
Could you
Go ahead, Ala.
multiply each by 4 on that side?
Yeah, on top and bottom of this fraction by 4. So then this is now 16 pi, and then this is just 4. So what's 3 pi over 4 minus 16 pi over 4? Who can tell me that? Theta equals 3 pi over 4 minus 16 pi over 4. What do I get, Emerson?
13 pi over 4.
-13 pi over 4. So that is one other answer. If I kept this going this way, I would get -13 pi over 4. Then I go back to my equation. I'm just going to go over here. Theta equals 3 pi over 4 again. What if I plugged in plus 2 pi times -1? That's 3 pi over 4 minus 2 pi. And Allah told us multiply on top and bottom by 4 before. So I'm going to make that 8 pi over 4. So who could tell me what is 3 pi over 4 minus 8 pi over 4 going to give me? What angle will I get for that? 3 pi over 4 minus 8 pi over 4 is what angle, Victor?
Can you repeat the question?
It's this over here. You had your hand raised, so unraise it when it's not time for you to participate. Go ahead, Jispel.
-5 pi over 4.
-5 pi over 4. So that would be another answer if I kept the graph going this way. Then what if I fill in 0? 3 pi over 4 plus 2 pi times 0 equals 3 pi over 4 plus 0 pi over 4, really, because it's 0 pi, equals 3 pi over 4. I get the first answer I found. So this way you're not excluding it by saying like, oh, I'm going to start there, but add and subtract. Well, you're also going to add and subtract 0, so you keep that original answer. If I filled in +1, instead of -1, If I filled in +1, I'd have 3 pi over 4 plus 8 pi over 4. What would that answer be? Can anyone tell me what that answer would be? 3 pi over 4 plus 8 pi over 4. What would that give us as an answer? Going once, twice, sold to Lispel.
11 pi over 4.
Right, we'd get 11 pi over 4, and that would actually be this spot right here. That would be 11 pi over 4. And then all of these answers that we're finding are answers that if we plug them back in to the original equation that we got this from, they would make it true. That original equation is not an identity, it's an equation that's only true sometimes. When something is true all the time, it's an identity, and the directions are going to be verify the identity, okay? Or prove the identity. Or here is an identity. You can use this, right? Like sine squared plus cosine squared is 1. Here you go. Use this, okay? But what we're showing is we don't actually have to always do this. If they ask you to find all solutions, well, you would do this for the rest of your life if you tried to do it this way. So what we do is we just write our all solutions in equation form, and that basically is sort of like a big blanket answer, and it kind of covers all possible scenarios. The way the pi symbol gives you all the decimals of pi. The way the square root of 2 symbol, because square root of 2 is an irrational number. That means non-repeating, non-terminating decimal. We can't write decimals forever, so we have a symbol, square root 2. And that, as a package, tells you, this includes all the decimals, you don't have to write it. Okay? So I hope this explains why and helps you understand why we want to write answers like this sometimes and not just making a finite list, because when we're finding all solutions of something cyclic, we will be writing for the rest of our lives. Okay? So that's like asking, I don't know, what day something in the calendar year, and you're going to list it every single, over and over and over again, when you could just say like, no, it happens like every February 2nd, Groundhog's Day. Like, just you answer like that. You don't have to be like February 2nd, 1999, February 2nd, 2000, February 2nd, 2001. Like, no, you just say it always happens on February 2nd, the end. Okay. So if that was helpful at all, if you watch this on YouTube later, or if someone from another class watched it on YouTube, let me know. You get the gist. I'm not going to ask you to explain it necessarily back to me, but do you get it? Okay. Thumbs up. If you're like, you're talking alien language, what? I don't know what happened. Thumbs down. So I know to go over it again. Okay.